Hello everyone. Uh, in subject rock mechanics and strata control. Today we are going to discuss about the following topics. Like what are the different type of stresses, like vertical stress, lateral stress, and what exactly the definition of vertical stress, lateral stress, relation between vertical and lateral stresses, and then let's derive the relation between both vertical as well as the lateral stresses. Uh, then we'll try to analyze the stress distribution in 2D model, and what is in the 2D model, what is the normal stress and the shear stress, and stress distribution in a 3D model, and analysis of stress distribution in a 3D model, principal plane, major and minor principal stresses. Okay, these are topics which I'm going to cover as part of this video lecture. So before I continue, let's recap what we discussed so far. Like in the earlier video lectures, we discussed about the basic terminology used in rock mechanics, like stress, strain, modulus of elasticity, scope of rock mechanics is mining, and relation between different modulus of elasticity. And apart from these basic terminology, we also discussed rock burst, coal bumps. What are the various causes of rock bursts, coal bumps, and what are the preventive measures that we need to take, okay, to avoid rock burst and coal bumps. So hope you understand all these topics. Okay, if you are not following, okay, just please refer my earlier videos. Okay, let me continue. Right. Now, in this video lecture, the new topics which we are going to cover is one is vertical stress. The stresses, what exactly the vertical stress is? The stresses which are acting along a vertical direction are known as vertical stresses. So here, if you look at this diagram, okay, this is a block of rock mass. Here, the stress will be acting like this. Like this, stresses are acting like this, only in one vertical direction. So like this, like this. So these stresses are acting on this block of rock mass in a vertical direction. That's why these stresses are known as vertical stresses. The vertical stresses can be of compressive nature. In this case, it is of compressive. Otherwise, it could be of if the stresses are acting something like this. Like this, away from this. These stresses are called tensile. So the vertical stresses could be of compressive nature. This is of, if R is towards inside, this it is of compressive nature, or it could be of tensile nature. That's what exactly it is. So in the definition of, if you look at the definition of vertical stress, the stresses which are acting along a vertical direction are known as vertical stresses. The vertical stresses can be of compressive or tensile in nature. Okay, let's move forward here. Right. Next, lateral stresses. See, the lateral stresses in earlier slide we discussed about what exactly the vertical stresses. Next one is what are lateral stresses? The stresses which are acting along the horizontal or lateral direction is known as lateral stresses. So in the same way as we discussed earlier, they could be of compressive nature or tensile nature. So let's say the stresses are acting like this. They are of compressive nature. So it could be of like this. The stresses are acting like this. They are of what? Tensile nature. So far the definition which we discussed was what exactly the what you call vertical stress and what exactly the what you call lateral or horizontal stresses. Next, let's discuss further. This is for the lateral stresses. Next, what exactly the normal stresses? The stresses which acts normal to the surface. Normal acts normal to the surface is known as normal stresses. Look at here. In case of 2D plane, the stresses which are normal away from this one, these are sigma 1. This is of normal stresses. In case of biaxial, look at here, it is acting along the two planes. That's why it is called biaxial, two axes. Okay, biaxial stress, sigma 1 and sigma. And in case of triaxial, it will be acting on all the three directions, x, y, z. So it would be something like this. Like this. So this is of y-axis. X-axis. So in case of triaxial normal stress, the stresses will be acting along x, y, and z. Whereas in case of biaxial, it will be only along x as well as y. Whereas in case of simple normal stress, it will be any of unidirectional. Here in this case, it is along x. So this is about the normal stress. Mm, so this is about the normal stress. What exactly the normal stress? The stress which acts normal to the surface is known as normal stresses. Okay. So there are a lot of unidirectional, bidirectional, or along the three different directions. That's what exactly they are. Okay. Let's move. Next, let us find out what exactly the relation between vertical and lateral stresses. Lateral, nothing but horizontal stresses. So other the direction other than the uniaxial direction, other than vertical. That is called lateral. Okay. In this case, this diagram basically represents sigma 1 is a kind of what you call compressive forces, whereas the sigma 3, which is acting along the other direction, that is nothing but the lateral direction, that is of what you call lateral stress. So we know pretty well. Now we need to find out what exactly the relation. So in order to find out the relation between the vertical and the lateral stresses, we'll be using the what you call the principle of Poisson's ratio, definition of Poisson's ratio. What exactly the Poisson's ratio? See, as we discussed in earlier lectures, earlier lecture or earlier video lecture, okay, Poisson's ratio is equal to, it's the ratio of lateral strain to the longitudinal strain. If I take this as around x, y, and z, okay, lateral is nothing but, let's say the x direction is lateral and what you call this is longitudinal y. So lateral strain sigma x by what you call sigma or epsilon x by epsilon y. This is what exactly the definition of Poisson's ratio. Using this, we'll be finding the relation between them. See here, the effective strain along x-axis. that is epsilon x is equal to, we know what exactly the Young's modulus. Young's modulus is nothing but what? It is the ratio of stress to the strain. So if I wanted the strain, so the formula is the formula for strain is what? Strain epsilon is equal to stress sigma by E. So in the similar way, the strain along x-axis is equal to sigma x by E, and the strain along y-axis is equal to sigma y by E. But we wanted to find out, because if I wanted to find out the, what do you call, if I wanted to find out, just a minute. If I wanted to find out the effective strain along x-axis, so it is nothing but the strain along x-axis and the strain which is acting in the other direction, that is going to be a lateral strain. So so that's going to, in order to convert the strain that is along y-axis toward the lateral direction, we'll be using what? The Poisson's ratio. So what exactly the Poisson's ratio in the previous slide? In the previous slide, the Poisson's ratio is a ratio of lateral strain to the longitudinal. So I wanted to any strain along the what do you call lateral direction. What I should do now? I should multiply the longitudinal strain with the Poisson's ratio. The same concept I have used in the next slide. See here, I wanted to find out the strain along the lateral direction. That is nothing but say mu into sigma y by E. Whereas the sigma y by E is represent what? The strain along y direction. But I wanted to find out with respect to x, because if I take x is the, what do you call, the direction along which I wanted to measure the strain, the other directions are going to be what you call lateral. So lateral, because we need to get the lateral strain now. So in order to get the lateral strain, we'll be using the Poisson's ratio. So effective strain is sigma, what you call, epsilon x is equal to sigma x by E. There is nothing but the strain along x-axis minus mu into sigma y by E. This is a kind of what you call lateral strain, because since we have used Poisson's ratio. So in the above formula, epsilon x is equal to strain along x-axis, sigma x represent normal stress along x-axis, sigma y the normal stress along y-axis, and where mu is the Poisson's ratio. This is what exactly the relation between vertical and lateral stresses. Okay, let's move on. Let's derive the same relation. So in order to derive the relation between vertical and horizontal stresses, this should be strain. I need to find out the relation between vertical and horizontal strain. How to find out that? Let us see here. This diagram, it basically represents what? In a 3-dimension, in a x, y, z. Okay, sigma x is the normal stress acting along x-axis, and the sigma y is the normal stress which is acting along the y-axis, and the sigma z is the normal stress acting along the z-axis. So these are the different normal stresses. Look at here. So we need to derive the relation between the vertical horizontal strain to the lateral strain in different directions. So that means with the application of forces in a 3-dimension, I need to find out what exactly along x direction, what exactly the effective strain along x-axis, because in x-axis the force is acting like this, which is of tensile nature, and due to forces acting in other direction also, that would be having the corresponding effect along the x direction as well. So we need to find out what exactly the effective strain along x-axis. So let sigma x, sigma y, and sigma z are the normal stresses acting along x, y, and z planes respectively. This is what exactly is represented in this diagram. X, this is x-axis, this is y-axis, this is z-axis. Okay. Next, epsilon x, epsilon y, and epsilon z represents the corresponding strain along x, y, and z direction. So this is what exactly is. We know from the formula of Young's modulus. What is exactly the Young's modulus? It's a ratio of stress to strain. So Young's modulus is nothing but, let's see here, what exactly the Young's modulus? Young's modulus E is equal to what? It's a ratio of stress divided by strain. This is what exactly. So if I wanted to find out the strain, what I should do now? This is equal to stress divided by Young's modulus. So strain along x direction is epsilon x is given by what? Stress. Stress along x direction is nothing but sigma x by the Young's modulus. Similarly, the strain along y direction is equal to epsilon y is which is equal to sigma y by E. Here the sigma y is what? The normal stress acting along y direction. Similarly, in the same way, the strain along z direction, epsilon z is equal to sigma z by E. So in order to find out the effective strain, either x or y or z direction, we'll be using Poisson's ratio, the concept of Poisson's ratio. What exactly, as we discussed in earlier slides as well, like what exactly the Poisson's ratio? It is the ratio of lateral strain to the longitudinal strain. So lateral direction to the longitudinal strain. That's what exactly is. So from this formula, from the definition of Poisson's ratio, lateral strain mu is equal to lateral strain by longitudinal strain. Lateral strain by longitudinal strain. This is longitudinal strain. So now, so from this, what happens? I wanted to find out the lateral strain. So lateral strain is equal to mu into longitudinal strain. This is what is. Okay. Next, using this one, we need to find out what exactly. See, due to application of strain along, I wanted to find out the effective straining along x-axis. Along, see here, the lateral strain along x due to normal stress sigma y. Because I wanted to find out. Look at here in this diagram. I wanted to find out the effective strain along this direction. But definitely there would be impact of the stresses acting in the other direction as well. Yes, z direction as well. But I wanted to find out what the effective strain, the effective one, effective strain along this particular direction. I wanted it, and this direction I wanted it. So how to get that? So like this direction I want it. So this direction I want it. So there would be a corresponding impact of the stresses acting on the other direction as well. So whatever the what you call strain that caused by sigma y and sigma z, that I need to convert to the lateral direction, this direction, because what would be the effect of the normal stress that is acting in the other two dimensions? Look at here, the effect of normal stress that is acting in other two directions. In other two direction like these two, and I wanted to find out that effect along this direction, this as well as this. So this is a lateral direction, whereas this is a corresponding for every direction. It's a kind of longitude. So to find out this one, what we will do? See, we know that what exactly the Poisson's ratio. Poisson's ratio mu is equal to what? Lateral strain by longitude. So I wanted with what you call, due to application of the strain along y as well as the z directions, I need to find out what would be the corresponding impact along this direction, x along x direction. So in order to find out that, I will be using the Poisson's ratio, because this basically gives the longitudinal one in the with respect along y direction. But I wanted to find out corresponding effect on the x direction, which is a lateral direction. So using the definition of Poisson's ratio, lateral strain is equal to mu into longitudinal strain. So the lateral strain along x due to normal stress sigma y. So with respect to due to application of this, I wanted to find out along this one, this direction, and along this direction. How to get that? For that, see here, epsilon y dash is equal to, so mu into sigma y by. The same way, lateral strain along x due to normal stress sigma z due to application of this, what would be the corresponding effect along the x direction? This I wanted to find out. So for that, I will be using similar kind of concept like epsilon z dash is equal to mu into sigma z by E. Okay, let's move on. Now effective strain along x-axis is equal to what? Epsilon x minus epsilon. This is a lateral strain due to sigma y. This is lateral strain due to sigma z. So sigma x by, because I wanted to find out along x direction. So the straining along x direction is what? Sigma x by e. And the lateral direction, that I need to subtract it because I wanted to find out effective strain along x-axis. So sigma x by e, this is a strain, actual strain along x-axis, minus there would be the corresponding effect on this one, reduction in the what you call strain along the x-axis due to application of normal stress along y and z direction. So that I need to subtract it. So minus mu into sigma y by e and minus mu into sigma z by e. If I simplify this formula by taking mu by e as common, okay, the formula is going to be what? It will be simplified to sigma x by e minus mu by e into sigma y plus sigma z. Same way, the effective strain along y is equal to sigma y minus sigma x dash minus sigma y dash. This dash indicates the lateral strain. So sigma y effective strain along y dash. This must be sigma y dash. Okay, or sigma y. This is the effective strain is equal to what? Sigma y by e. There's nothing but strain along y axis because I wanted to find out along y axis minus the lateral strain in the other two directions, like mu into sigma x by e minus mu into sigma z by e. Okay, if I simplify this formula, it is going to be equal to sigma x by e minus mu by e into sigma x plus sigma z. Similarly, the effective strain along z axis is equal to sigma z or epsilon z minus epsilon x dash minus epsilon y dash. So epsilon z is equal to sigma z by e minus mu into sigma, because this is lateral strength. Okay, if I take what you call mu by a as common out of this equation, so the simplified equation is going to be what? Along the effective strain on z axis, epsilon z is equal to sigma z by e minus mu by e into sigma x plus sigma y. This is what exactly the derivation of relation between vertical and lateral strains. Actually, this is not stress. It must be strain. It should be strain. It should be strain. It is not that, it should be strain. Okay, so this is what exactly the relation is going to be. So problem. Okay. So there is some problem, technical problem. Let me check it once. Let's continue. So far we discussed the relation between what you call the vertical as well as the lateral strains. Okay, how to derive that. Now let us analyze in a 2D block. Okay, what are the stresses that are acting? Okay, in this case, what you have taken, this is along x-axis and this is along y-axis. So definitely, whenever the stress which is acting normal to the plane, they're called normal stresses. Look at here, sigma x, sigma x, sigma y, and sigma y. Okay, these are all called the normal stresses acting in a 2D block, okay, along x and y directions. Whereas the tau xy and tau yx, they represent the corresponding shear stresses. Okay, the tau x with the notation of tau xy is nothing but this is a shear stress. The first one is represents the plane on which this stress is acting. Y, the second term on this represents the direction in which it is acting. So in this case, the shear stress is acting on the x plane, along which direction? Along y direction. Along y direction. I repeat. Okay. Look at here. In this, let's analyze the stress. The stress is acting on a 2D block. Okay. So the stresses which are acting normal to the plane, they are known as normal stresses. These are all normal stresses. These are all called normal stresses. And the stresses, see here, it is acting towards sigma x direction. That's why it is called. This is x, right? This is sorry. This is one direction, and this is another direction, right? So as it is represented here, this is sigma x, and this is sigma x, and this is sigma y. These two, x and y direction. So this is x and this is y. So the stresses which are normal to the surface, they are known as normal stresses. Next one, the stresses which are acting on the plane. Look at here, this one. Okay. Like this, like this, like this. Sorry, it is like this and it was like this. So they are called shear stresses. It is represented by a symbol tau. So the notation of tau xy, it represents what? This shear stress, the first one, it represents the plane on which it is acting. And the second one, it represents, second letter represents the direction in which it is acting. So in this case, it is acting on x plane. In which direction? Y direction. So that's why it is called tau xy. If you look at here, tau yx, that's nothing but this shear stress is acting on the y plane because this is y-axis, right? On the y plane. Along which direction? X direction. That's why it is called tau yx. Same way here also, this is tau xy, whereas this is tau y on y plane acting towards the y direction. That's known as tau yx. Okay, okay. This is how exactly the what you call basic diagram of the stresses acting on a 2D block. Okay, so in this case here, sigma x and sigma y are the normal stresses acting along x and y, whereas tau x and tau yx are the shear stresses acting along the different planes. Generally, the value of tau xy it is equal to tau yx. That's what exactly this is. That's how generally it is. Generally, the value of the shear stress acting on the x plane towards the direction y is equal to the shear stress acting on the y plane acting towards the x direction. Both must be generally they will be equal. They are equal. Generally, they are equal. Okay, this is about in brief about the stresses acting on a 2D block. Okay, let's clear this. Clear all drawing. Hold it. getting angle. Fine, right. So we did just discussed about notation of different stresses acting on 2D block. 2D block. Okay. Look at here the sign convention for shear stresses. Shear stresses. In case of normal stress, these stresses which are normal and they are of tensile nature. There's nothing but which are acting away from the body. They are of tensile. Okay, they are taken as a positive, and the stresses, normal stresses which are of compressive nature, they are taken as negative, because these conventions we'll be using in the upcoming lectures actually. So we must understand what kind of convention that we need to use while analyzing the stresses acting on a 2D block. Okay, so I repeat, look at here the stresses which are of away from the block of block two-dimensional block. Okay, in this case they are all these normal stresses are away from this. They are of what? Tensile nature. If they are towards the block, they are of what? Towards nothing but like this. They are known as compressive. So generally the convention that we use is the normal stresses which are of compressive, they are taken as negative, and the normal stresses which are of tensile, they are taken as positive. In the same way, clear. Same way, the shear stresses which are acting on a 2D block, if they are of what? Clockwise direction. But in this case, this here, this is called clockwise direction, right? Like this. So tau yx, they're acting on the clockwise direction. They are taken as positive. Look at here. The shear stresses which are tending to turn the element in clockwise direction, that's taken as positive. And whereas the shear stresses which are acting in the counterclockwise direction, counterclock is nothing but what? Counterclockwise. So clockwise direction. Let me take this. Yeah, like this. They're taken as positive. If they are acting in the other direction, they're taken as negative. Okay, let's go back to the previous slide. Okay, here. In this case, stresses which are acting, this is a clockwise direction, they are taken as positive. The stresses which are acting in the opposite direction, like this, they were taken as negative. So that's what it is. Okay. So okay, so that's what it is. Next one is okay. Now that's about the stresses acting on a 2D block. Next, analysis of normal stresses, shear stress along a failure plane, which makes an angle theta. In this case, look at here. This is a 2D block as we discussed in earlier slides. Okay, 2D block or which sigma x and the sigma y are the normal stresses. Tau xy and tau yx here both are taken as equal because we assume that they are equal. So tau xy and this is also instead of yx we used tau xy because it's both are equal. Okay, it doesn't make any difference. Now this is the failure plane. In this case, let's say analysis of normal stress and shear stress along a failure plane. The plane is making an angle of what? Theta. with the vertical. So in this failure plane, sigma theta is the normal stress and tau theta is the corresponding shear stress because it fails like this. So it fails like this. That's the reason. And along the failure, this we need to analyze. Okay, hope you understand that. Okay, I repeat, in a 2D block, sigma x and sigma y are the normal stresses acting on the planes, and the tau xy and tau yx are the corresponding shear stresses. And assume there is a what you call failure plane P, PC, or failure plane P, which makes an angle of theta with the vertical. So definitely, in order to fail this plane along this particular direction, okay, in order to what you call fail this block along this particular plane, so there would be corresponding normal stress and the corresponding shear. So the normal stress acting on this plane, failure plane, is sigma theta because since it is making an angle of theta, sigma theta, and the corresponding shear stress acting on this plane is tau theta. So we need to find out this one. Okay, so the formula for the normal, see here, equations of normal stress and shear stress acting along the failure plane. So sigma theta is the normal stress acting on the failure plane is equal to, we know the values of sigma x, sigma y, and tau xy. These values will be like, and the relation between them is, see here, normal stress along the failure plane, sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos theta plus tau xy into sin 2 theta. I repeat, sigma theta is equal to tau x plus tau y by 2 plus sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sin 2 theta. This is what the formula to what you call to calculate or to determine the normal stress acting on the failure plane, that is sigma theta. And the corresponding shear stress, tau theta is equal to sigma x minus sigma y by 2 into sin 2 theta minus tau xy into cos 2 theta. So these formulas will be using to determine the normal and shear stresses acting along the failure plane, which makes an angle of theta with the vertical. Okay. Next one, how to find out the maximum? Because see, in the along the failure plane, okay, since we got two equations, so one is equations for the normal stress and the shear stresses acting along the failure plane. Now we need to find out what should be its maximum value and what should be its minimum value. Means the maximum normal stress that will be acting along the failure plane and the corresponding minimum, and what exactly the corresponding what you call the shear stress that will be acting on the plane. So in order to find out that, what we will be doing is, okay, see here, these equations gives two values of 2 theta that differed by what called 180 degrees. Okay, hence the planes on which the maximum minimum normal stresses accurate to 90 degrees apart. So in order to find out this one, so generally in mathematics we'll be computing the corresponding derivative of this. So we know the value of sigma theta is equal to, as we discussed in the previous slide, sigma theta is equal to, that's nothing but the normal stress acting on the plane which makes an angle theta. Sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy into sin 2 theta. Okay, this formula we'll be using and trying to find out what exactly this one, same formula. And we try to, if we derivative, we need to find out the derivative of this one with respect to theta is equal to sigma x minus sigma y by 2 into, this will be a constant because we need to find out, trying to find out derivative of this one with respect to theta. So cos 2 theta is equal to minus sin 2 theta by 2 because 2 theta is there divided by 2. That's the reason, minus 1 by 2 into, okay, sigma x minus sigma y by 2 into cos sin 2 theta into 2. Okay, plus, okay, tau xy, which is a constant, and sin 2 theta is nothing but cos 2 theta, and derivative of 2 theta is 2. So this is how it is, which is equal to 0. If I simplify this one, we'll be getting what, tan 2 theta is equal to 2xy by sigma x minus sigma y by 2. So from this we can find out what is the value of theta now. Theta is equal to tan inverse right, 1 by 2 into tan inverse of 2 tau xy by sigma x minus sigma y. So from this, because after simplifying this equation, finding out after finding the derivative of this one, we can find out what would be the angle made by the plane in which the value of the normal stresses either maximum or minimum. That angle we can calculate from this particular formula. Okay. Now let us find out what is what you call the corresponding maximum and minimum stresses, minimum normal stresses. So the maximum and minimum values of stresses acting along failure plane is given by sigma x, because in the same way, if simplify the formula, same formula further, we'll be getting sigma 1 is equal to, this is sigma 1 represents the maximum value and sigma 2 represents the minimum value. Generally in other books they will be using sigma 3. Okay, sigma 1 is equal to 1 by 2 into sigma x plus sigma y plus 1 by 2 into square root of sigma x minus sigma y whole square plus 4 tau xy whole square. In the same way, the minimum value, that is nothing but is equal to 1 by 2 into sigma x plus sigma y minus 1 by 2 into square root of sigma x minus sigma y by sigma y whole square plus 4 tau xy whole square. That's nothing but the maximum or minimum values is nothing but, see here, sigma x plus sigma y by 2 plus or minus, because plus indicates the maximum, the minus indicates the minimum. Okay, and 1 by 2 into square root of sigma x minus sigma y whole square plus 4 tau xy square. Okay, here, see here, the sigma 1, sigma 2 are termed as the principal stresses on the system. Now we need to find out, because so far from this we could able to find out what could be the value of the failure plane. Okay, because since we find the normal stresses and shear stresses acting on a plane which makes an angle theta with the vertical. So sigma theta and tau theta we find out. Then we find out what would be the angle made by the plane in which the value of normal stresses either maximum or minimum. So the angle that we can obtain, okay, by differentiating the equation with respect to theta and equal to 0, and upon simplifying this, we get the tan theta is equal to tan 2 theta is equal to 2 tau xy by sigma x minus sigma y. From this we can find out the angle made by the plane. Next, upon substituting this value of theta in this equation, we'll be getting either maximum or minimum value. So the maximum value sigma 1 is equal to sigma x plus sigma y by 2 plus 1 by 2 into square root of sigma x minus sigma y whole square plus 4 tau xy square. And the minimum value is there is a minus. Okay. Now, what is exactly the principal plane? So we derived, see, the plane, okay, principal plane is nothing but the plane of failure along which the values of normal stresses are maximum, either maximum or minimum. So that plane is called principal plane. That plane is called principal plane. So the maximum and minimum values of stresses acting on the principal plane are also known as major principal stresses and minor principal stresses. That is nothing but sigma 1 is the major one. Generally, some other books, instead of sigma 3, people will be using sigma 3. Okay, here we have used. So sigma 1, in this case, sigma 1 is the major principal stress and the sigma 2 is the minor principal stress. Since because they are the maximum and minimum stresses which are acting on the plane, that the plane in which the values of normal stresses are either maximum or minimum, that is known as principal plane. Okay, in the principal plane, the value of shear stress is equal to 0. Nothing but the plane is going to be principal. Okay, principal in which the normal stress is either maximum or minimum, there will not be any corresponding shear stress acting along that particular plane. Hope you understand. Hope these concepts are very clear. That's all from my end as part of this video. Thank you very much.